Hey class, so some of you have expressed that you're running into difficulty on the last couple problems on this Wiley homework, and that makes sense because the last two problems really are cumulative problems, adding stuff from chapters 18, 19, and 20 all together. So let's think about what we got going on here. We have a situation where we're told some stuff. I've labeled, we have our pressure at point B given to us, we have the volume at point B, which is also the volume at point A given to us. And we're basically told that the volume at C is 8 times VB, so we know the volume there. We do not know what the pressure is at points A and C, but we do know that they're the same. And we're given our N value, the number of moles, as well. And what are we asked to determine? Based on those things, we're asked to determine how much heat is added to the gas, how much heat leaves the gas, how much work is done by the system, and what the efficiency is. These are all the things we're asked to determine. Well, boy howdy, right? That's a good things to ask. So let's consider how we can figure these out. So work, all right, we know that work is going to be equal to, that's a terrible equal sign, so I'll retry that. Our work is going to be equal to QH minus QC, but really the magnitude difference, right? Since QC is exiting, so it's going to give you a negative value, you want the magnitude. Alright, so if we can find the answers to A and B, the QH and QC, we can determine what the work is, and then once we know those, efficiency will become easy, right? Part D asks us for efficiency, which we know is just going to be equal to the work over the heat added. So the question then is, how can we find QH and QC? So let's look at our transitions over here. We have three transitions, right? We have A to B, we have B to C, and then we have C back to A. All right, so A to B we can see is a isovolumetric transition, or an isochoric transition, where we have constant volume, right? So here we have constant volume. So what that means then is the heat exchanged during that transition, so the QAB, we know is going to be heat being added to our system, so that's at least part of it, and we know based on our handy-dandy equation sheet or from memory that the heat exchange during a constant volume transition is CV and delta T. Cool. That sounds good. Now B to C, that's adiabatic. Oh boy howdy, that's easy enough. We know the heat exchanged with a system during adiabatic transition is always going to be 0, so that's easy enough. And then from C to A, here we now have constant, there's a S missing, there we go, constant pressure. So we have an isobaric transition, and we know for constant pressure, that's when our heat can be quantified as Cp and delta T. Alright, so we see that heat is exiting during the transition from C to A. I know that because of the nature of the transition here in the negative direction. Alright, we're going to be dropping in temperature, so that's going to be a negative value, that's heat exiting. And then QH, I know this is going to be our heat added as we raise in temperature. We know that we're going to be having to add heat to cause that transition to occur. So that's how I know what we got going on. So the question is, if we can find out CV and delta T and CP and delta T, we can solve the entire problem. Okay, well that's fun. How do we do that though, right? We're not given anything about temperature. Okay, so what I want to consider, well, I guess first let's think about what CP and CV are. So our degrees of freedom in this problem, I guess I could have labeled that as a given, but we're told that it's a monatomic gas, so we know F is equal to 3, so we can observe that CV, we know, will be 3/2 R, and we know CP is going to be equal to 5/2 R. Cool. So that's easy enough. I'll fix this to actually look like a 2, otherwise it looks like 5 over gamma, which is not accurate. Okay, cool. So what about delta T? How do we find our change in temperature? So if we think about it, all right, we know for these constant pressure and constant volume transitions, we can observe the ideal gas law. So the ideal gas law tells us PV equals nRT, and so what that means is that T can be written as PV over nR. Alright, so what that implies then is that our change in temperature, in this case, well, in either of these two cases really, what it's going to be equal to is our volume, or our amount of gas, our N value, is not going to change. R is a constant, so I can pull those out. So I have 1 over nR multiplied by, then delta T would be delta PV, right? So that's going to be P final, V final, minus P initial, V initial, is what our delta T would be equal to. Okay? So again, I'm going to keep moving down. Alright, so what we're looking at in part A, for example, of this problem, maybe I'll switch colors here. So for part A of this is when we're trying to find QH, and that's, again, CVN delta T. So what we can find is that our QH is really just going to be equal to CV, which is 3/2 R times N times delta T, which is 1 over nR, and then we're multiplying that by our P final, V final minus P initial, V initial. So if we scroll up really quickly, we're again looking at this transition here. So our final is location B and our initial is location A. So what we have is we have PB times VB minus PA times the volume, and since it's constant volume, that's also VB. And so we can observe, look at this, alright, our N's and R's cancel out. We can pull out that VB if we would like, and we find that QH is equal to 3/2 VB multiplied by our change in pressure PB, which is given to us, minus PA, which we don't have. So if we get PA, then we can solve for our QH, okay? Then part B, you do a similar thing, right? So for part B, we have QC equals CPN delta T. Now we're looking at this transition here from C to A. And so what you will end up with, I'm going to skip some steps to save some time, but you should be able to do the same steps, subbing in for delta T. You should get to an equation that looks like 5/2. Again, your N's and your R's will end up canceling out. You now have a constant pressure, PA, and then you're multiplying that by the change in volume. And so what we really have is what we've called VB, the volume at point A, minus the volume at point C, which is 8 VB. Again, if you're wondering where I'm getting those values, that comes from right here. Alright, so the volume at point C is 8 VB, and the volume at point A is just VB. Okay, so you could even reduce that, right? Because VB minus 8 VB just gives you negative 7 VB. Alright, cool. So we got that going on. Now the question is, though, in both of these situations, we cannot solve until we determine what this pressure is. We have everything but that pressure. We solve for that, and then we are golden, all right, like my pen that I just drew. Okay, so how do we go about getting that? Well, to get that, the key is looking at the transition that we have from point B to point C. All right, so I'm going to scroll back up here. So if we look, our last transition we haven't considered is this adiabatic transition. Okay, so we have pressure at point B and volume at point B, pressure at point C and volume at point C, and it's an adiabatic transition. So what we can do is we can use the, I'm going to go over here actually to create some new space. Maybe I'll look at a new color. So for the adiabatic transition, again we're looking at from point B to point C. What we know, as we saw in our homework over the weekend, is that we have this relationship that PB times V B to the gamma is equal to the pressure at point C times the volume at point C to the gamma power. So we're solving for the pressure at point C, so you can rewrite that as the volume at B over the volume at C to the gamma power times the pressure at point B, which is given to us. All right, and so we can continue to solve, and our pressure at point C, which recall is the same as the pressure at point A, those are the same values, is going to be equal to our volume at point B divided by 8 times our volume at point B. That's what our volume at C is, right? Just as we saw over here, okay? To the gamma power multiplied by the pressure at point B, which is given to us in the problem statement. And keep in mind, gamma, monatomic gas, we're looking at 5/3 is the value for gamma. So you should, from here, be able to solve for PA, plug it in over here, in case you're wondering where I'm talking about. Maybe I'll zoom out just a little bit for you. So you can plug it in over there to find QH. You can also then plug it in over here to find QC, and once you've done that, you can very easily determine the last two parts of the problem, right? Because C asks you for the work, which is going to be equal to the magnitude of QH minus the magnitude of QC. Again, magnitude, since QC will be negative. And then part D is just your efficiency, which is the work over QH. Alright, so I hope that's helpful. If you guys have extra questions, let me know. This general process and some of the tricks and tools that we used going through this problem are very similar to what you're going to need to be thinking about and doing for problem 34 as well. So let me know if you have any questions, and I hope that helps you get to a solution. Have a box-worthy day.